Good morning, everybody. Good morning, Twitchies. Let's hope we have good enough Wi-Fi for streaming. Wi-Fi for streaming. Wi-Fi for streaming. Wi-Fi for streaming. You guys see that where Cartman glitches out on the Zoom call? All right. So I was going to do something today. It was nice and peaceful, and I thought that I would share it with you streamers. I got tea prepared for me by the lovely Alex. Made me tea. I'm very happy. Welcome my streamies. Welcome my streamies. As long as I'm not, blocked like the New York Post story, you guys can all come in here and watch me stream. Yo, what up? All right. So, we're getting back into we're going to do some coding. And you guys love when I do coding. We're going to try to write MNIST. We're going to try to write deep learning from scratch. And we're going to see, and you can all watch me embarrass myself with how little calculus I know. So I've already done a little bit of it. This was done off stream, and then I'm like, you know what? This will be a nice stream for everybody here. So, I just went to the MNIST dataset page. And here are the files that are available. I just wrote this little fetch function, which here we can restart this kernel here. We're going to do it without PyTorch and without TensorFlow. We're going to do it with nothing. I wrote this little fetch function here, which will fetch them, and then we can we can do like an im show, an x train. Oh look, it's a 5. Yo, let's see if it's a 5. Yo, look at that, it's a 5. All right, we're doing well. All right, cool. We're gonna try to write this entirely from scratch, and we're gonna see what error rates we can get. So who knows how to write backpropagation without using a library? Maybe we should first write it in a library. Hype train incoming. Wow, that was fast. All right, you know what? Let's first get just started and do a little PyTorch, just because we can. So what am I going to call my net? We're going to call it BobNet. Let's say, what is it? Torch. All right, so let's just first write it in Torch. We'll import Torch NN. I'm going to write BobNet as a Torch. Let me just make sure that I'm not blocking that part of the screen. We're actually going to move me. What do you guys think? We're going to move this over here, and we're going to move, and we're going to move me up here. Yeah, there we go. I think that's nicer. Cool. All right, I moved. I know I moved. So yeah, we're going to start with a little torch. Def init. It's just relaxing on a beautiful Saturday. I went to Blue Bottle this morning, got some nice coffee, super BobNet self, and you know what? Doing these like simple exercises, it never gets old. So we'll just say, we'll call it L1 nn.linear. We're gonna go from 784 down to, let's say, 128, and then we're gonna have an activation function. We'll use a good old ReLU. And we'll have another linear layer, which takes us from down to 3, and we'll use logarithmic softmax, so that shouldn't be a problem. We got to write the forward pass. You take in an x, you apply layer 1 to it. No. Why is that? This used to be better. I feel like I used to hit that, and it would not do that. It would just go back to the beginning of the line, but whatever. All right, so we can instantiate a BobNet. We'll say model equals BobNet. All right, now I can run my model on, say, we got to do a lowercase model. On, say, x train 1 through 10. Okay. Forward takes 1 positional argument, but 2 are given. Oh, I forgot the self. You always need the self. Don't forget about the self, people. ND array has no, we got to turn it into a tensor. All right, good. The given NumPy array is not writable, and PyTorch does not support non-writable tensors. Oh, that's a tragedy. Let's just do a .copy in there. because I did it from buffer. It's actually from a Python buffer, so it's not writable in NumPy. Expected object or scalar, but got type float. Oh, we're gonna have to turn these into floats. Okay, so we'll just do a float. Wow, this is harder than I thought. Wow, I'm being a noob here. All right, don't be a noob. All right, let's go, let's go, let's go. Gonna reshape this into that times that. All right, good. So we got some stuff out. Let's write a quick training loop for this. How many epochs do we want? For I in range 100. Let's set our batch size equals 32. Do something like np random randint. Yeah, I can say something like size equals. Perfect. Shape. Size equals 23. Size equals BS. BS is not defined. Oh no. We'll say samp equals that. Let's just do 2 for now. Print samp. Okay, good. So those are our samples. So we'll just sample from the array. We'll call this just X. We'll run the model. We can't just run it on X. We got to run it on that. MPND array is not. Oh. Okay. We'll say Y equals Y train subsamp. All right. So we have our out equals this. NN cross entropy loss in PyTorch. Yeah, this. So I think we just want to say loss out y. Is that exactly what I want? We'll call this loss function. First, we're going to write it in PyTorch, and then we're going to try to replicate the same thing without the use of PyTorch, and that's what's going to end up taking too long and be too hard for us to do on the stream. Int object is not callable. Who's trying to call an int? Who's calling an int? Don't call ints. Oh, because I got to make that a tensor. You know what? I'm actually going to move this here. And then here we're also going to say torch tensor y train samp. Model X. Oops, it goes after the tensor.
I didn't get that. Could you try again?
No, Siri, bad Siri.
Sorry.
No Siri, bad Siri. Okay. What do I want this to be? Long? Can I make it long? Yeah, it's long. Okay, cool. Let's check our loss. All right, perfect. So now we just got to do backwards. So we'll say loss dot backwards. And we're going to need to write a, we're going to need an optimizer. NN PyTorch atom. Yeah, torch optim. So something like optim equals what? Torch.optim.atom sub model.parameters. That should work. And then, oh, we're gonna have to zero the gradient. If we didn't zero out the gradient, did I forget to do zero grad in one of my examples? I think I did. That might have been why I had such a problem learning models that output 2, but that was different. Okay. Import from TQDM, import trange. Let's make it a trange. And then actually, oh, who's ready for some walrus? Oh no, don't tell me I only have Python 2. No. What Python version do I have right now? get Python version. Oh, you know, you guys know I love the walrus operator. You know, let's just try a walrus and see if it's going to work. Come on, walrus, I believe in you. The walrus is my favorite operator, and anyone who doesn't believe in walruses is a liar. Yeah, I got a walrus. All right. So look, now I see, you know, I can just use beautiful things like t.set description. Let's say like loss 0.2f, like that. Yeah, I know there's like a better way to write that in Python now. Dot item. Oh yeah, wow, that's so nice. Oh, I love walrus operator. Who loves walrus operator? This guy. All right. Let's also check the accuracy. So let's say torch.argmax out dim equals 1. Say cat equals that. Let's not do that. Let's see if I wrote something right. Okay. And then what we want to know with accuracy is cat equals y. Dot sum. Accuracy equals that. No, we want to actually mean on that. Oh, I can only calculate means on floating points. Oh, I gotta make them floating points. Okay, good. They're floating points. All right, good. Accuracy. And we'll say here accuracy.item. All right. You can do that, right? Perfect. We want to make some quick graphs up. I know you guys like graphs. Who likes graphs? You like graphs? Graphs look good for the YouTube, right? Alright, let's go. We'll call it losses. Accuracies equals that comma that. Say losses dot append loss. Accuracies dot append accuracy. And then let's just throw a plot down here. Plot loss, plot accuracy. What? Oh no, we got plot losses and accuracies. All right. Yeah, buddy, let's get it. All right, so let's go for 1,000 steps. 32 is a good batch size. Run. Train. Oh, loss goes down, accuracy goes up. Oh, let's not. Let's clip that to... what can I say? PLTY lim. Well, accuracy doesn't go higher than that, so let's just say like -1. Does that look good? Yeah, cool, but 1's a little low. Let's go to 2. All right, cool. Beautiful. Loss goes down, accuracy goes up. Everybody's happy, right? Is everybody happy? Good. I'm glad if everyone's happy, you know, and I'm happy, and we're all happy. All right, let's lower that only to 100. Boom, boom, let's go. Okay, good. Wow, accuracy goes up so fast. Oh, it's unbelievably fast. 300, 400, let's go. Okay, cool. So we wrote a little trainer in PyTorch, and then let's write the final evaluation. Who can write this quickly? Model. I don't want to copy that code. We're going to copy it. Let's do it. Model, torch tensor, x test, reshape float. And then we want to take out, and we just want to do an argmax on that. Dim1. We'll say y test threads. let's just throw a .numpy on there so we're not testing it in Torch. Y test equals y test creds.mean. I think that works in NumPy. Cool. Oh, we got 90%. Good, that's an A. All right, who's glad we got an A? I'm pretty glad about my A. All right. Evaluation. Training. Model. All right, model training evaluation. No, we only got an 88. That is more mediocre. We're not going to write Atom. Let's change it over to SGD. Oh, we got to give it a learning rate for SGD. I can't use the default one. Is that a good learning rate? That was not a good learning rate. That did not learn. Did not learn. Okay, let's try a tinier learning rate. Let's actually initialize BobNet up here so we don't... Does SGD even work? I think we got to give it some momentum too. You know what? We're going to do it without momentum because we're going to implement this from scratch in MNIST from scratch. You know what? Let's just be explicit about our lack of momentum. No momentum. That's right. Okay, how well do we do? Wow, we got an 87. Oh, that's a B. That's a B. Is that a B plus? I got a B plus. I don't know. It's been a while since I've been in school. Is that a B plus? Oh, 91. Oh, that's pretty good. Let's up our BS. We need more BS. Just like, you know. All right, let's go. Let's go. Let's go. Oh, 93. Oh, that's a pretty good number. Who's pretty happy with that? All right, that's too many. Let's do less steps. 91. Oh, I do 1,000 steps, I get it more. All right, how long does that take? Only a few seconds. All right, we can be patient. 92. All right, who's excited? We got MNIST. Can I do losses, comma accuracies? No, this is going to complain to me, isn't it? Oh, I should have tested that without having to do that. Yeah, great. High quality shit. Oh, wow, it's like losses versus accuracies. Can I do that? Is that good? I want to save that line. You know, I don't like writing crappy code. Oh, that's terrible. Oh, that's not what I want to do. You know, yeah, you guys probably in the chat right now that I'm not reading are probably like, oh, you just got to put the squiggly. You put a semicolon and then it does it. But we don't have any semicolons. My keyboard doesn't have that. My keyboard is actually out of semicolons. Oh, that too is aggressive. Let's go 1.1 and minus 0.1. Let's really get a nice graph. Oh, that's a beautiful graph. What do we all think? Oh, that's so beautiful. All right, let's evaluate it. All right, we're getting 93s, yo. That's an A. That's not even an A minus. I'm just out of that A minus range. I mean, a 95 would be nicer, you know? But I'm pretty happy with that. All right, so that was it in PyTorch. We're never going to do it in TensorFlow because TensorFlow is a piece of garbage. And we don't use TensorFlow around here. We use PyTorch. All right, let's just check in on chat before we get started on the heavy math part of this where you guys can watch how bad I am at calculus. We're doing MNIST from scratch. All right, you know what? Let's try 256 for the BS just quickly. Does it do a lot better? No, it doesn't do a lot better. It does marginally better. BobNet. BobNet is probably the crappiest MNIST. Yeah, no, that's hard. We're going to do this all from scratch. Oh, we got frame drops? Oh, no, we don't got frame drops. It's looking pretty good. Hell yeah, math. Let's go, boys. Let's go. Do you think we can re-implement this thing without the use of PyTorch? The mug is sick, right? Alex, they like your mug. Deep learning is absolutely not a scam. We're going to win self-driving cars. I probably totally missed a hype train. I'm sorry for missing you guys, but without PyTorch and without NumPy, whoa, that's like giga hard mode. Yo, we're not going that far. We're definitely not doing it in C. We're doing it in Python. We're going to do NumPy, and we're going to show that we know math, and we're going to see if we can replicate these amazing MNIST results, truly amazing MNIST results. What do I have? Can I not use requests? What do you want me to do in C? You want me to use suck it? want me to use socket, receive, and send? You want me to write an HTTP? Oh, you guys would love that. Oh, you guys would love that. Oh, I bet you would. I bet you'd love it if I didn't use requests and I like opened port 80. Oh, you want me to write some TLS negotiation? Oh, yo. By the way, can we talk about how the walrus is the sickest operator in Python, and anybody who isn't pro walrus is a loser? That's how I feel. I'm the biggest Python 3 shill. You know, you can put some clips of me next to me from the past talking about how Python 2 was great and now shilling for the walrus, and you can be like, he's a flip-flopper like John Kerry. And you guys could do that, and wow, that's some sick branding if I'm still calling John Kerry a flip-flopper 16 years later. Damn. All right. The Archie flip-flopper. No, I can't read chat. You guys distract me. Yo, the walrus is bad. You're lucky you're a subscriber. All right, please subscribe to my channel. It's only for my love of the subscribers. No, that's not. No, I'm not even playing. This is the new Twitch channel. I'm just doing this because like I was gonna write this today, and it's more fun to talk to myself, and you guys give me an excuse to talk to myself. Lex Friedman Part 2 coming soon, boys. I think I did well. I don't really remember what I said. Lex Friedman is a great guy. People like him are going to save the world. Hard Target 4, thank you for subscribing. No, I don't know when it'll become available. Lex has a lot to do. I hope his social media app can work. What I told him about that was I think it's a harder problem than self-driving cars. I know how to solve self-driving cars. I don't know how to solve human nature. Okay, I'm never doing Jerry. All right, we got to hide the chat. You guys distract me. Sorry, chat. You guys are a distraction. Wow, you know, you're just going chat. You get in a whole chat mindset. You get out of a coding mindset. You see, that was fun. You know, you guys could like clip those like 30 minutes, and it's like, you know what? Guess what? I don't have BobNet written in another window, unlike certain scam streamers that I know who write all the code beforehand. You know, scam streamers. Don't be a scam streamer. You just gotta disclose, man. Like everybody, you know, it's like freestyling. You know, this is real off the dome shit. You know, and like battle rap is great. You know, like the pre-written stuff. You know, I look like the type to win a Pulitzer Prize until I pull it surprise and bullet your eyes, right? Like you never came up with that shit, you know, in the moment. So that's why it's nice that it's pre-written. But you know, you just got to disclose. Everyone's got to be on the same page about that kind of shit, right? And then we're all good. You know, no sins as long as they're permission. Preach Kanye West. All right, let's go. Okay. So what is a linear layer? Does everyone know what a linear layer is? Oh, well, actually, bias equals false. I don't really want to write that bias. What, does this need a bias? I don't even think this one needs a bias because I'm doing, yeah, that's fine. Actually, that's an interesting point. I don't think I need biases if I'm using, well, no, actually, that's not exactly true. Let's see how the accuracy does. Pretty much the same. All right, we're not going to write biases, but we should write biases at some point. Wow, it doesn't matter at all. I'm trying to think what happens if I do that without a bias, if it matters. Probably does, but okay. So what is a linear layer without a bias? It's just a matrix. L1 equals np.array. Let's first see if we can copy. Let's first see if we can copy the weights from Torch and get the same result. You know, is NumPy array normally, what type is this? Int 64? Oh, well, that's not, I meant to say MP zeros. Float 64, that's disgusting, NumPy. Float 64s are disgusting, and you should be ashamed for making that the default type. Scientific computing is bullshit. Everyone knows float 32 is all the float you... Wait a second. I'm only saying that because of NVIDIA only supporting float 64 on the expensive GPUs. I've never actually tried training a float 64 neural network. I wonder if they work great. Yo, You think if we up the accuracy to float 64, everything's just going to become super precise? Now, it probably means you were lazy with your gradients. Yeah. Int 8 works. You just got to add noise. Oh, yo. All right. Guess what I bought for tomorrow? And this is a little... I bought Oculus Quest 2. And I don't have a Facebook account. So you all know what that means. But I bought a Quest 2. I don't have a Facebook account. I don't know. Am I not going to be able to use the hardware I paid for? Probably lucky. I would love your $5,000. I would appreciate it. I would frame that check. Check from the Oculus founder for jailbreaking the Oculus. Yeah, that'd be cool. All right. But enough daydreaming. Let's focus on writing this. Okay. So we have model. I love PyTorch, by the way. If I haven't expressed my love for PyTorch, you know, I can just say stuff like that. Oh, that's so beautiful. That's so beautiful. Am I going to have to detach? Oh, you have to detach NumPy. You can't just NumPy. You have to detach it from the graph first. I don't really understand what graphs are, but I do know. Oh, wow, they got it twisted. All right, let's get it twisted. Okay, we'll call this the init the network. No more PyTorch here. Now that's a lie. We're not going to lie. Copy weights from PyTorch. Yeah, that's right. Don't lie. That's not actually what I want to do. Like, how do I assign the... Does that do what I want? Is that still the original array? What? There's a Python way to do this. How do I get the memory address of something in Python? Get object memory address Python. It's not rep id. Gotta check your id. All right. Okay, that is the same id. So, but now if I do this, it's going to have a different id? Yeah, okay, so I want to do that. I want to actually copy in the weights. I don't want to not copy in the weights. All right, let's go. Okay, so now if I want to actually evaluate this, let's write a NumPy forward pass. We'll call it forward x. We want to say, what is it? X dot L1. And it's going to look very similar to the PyTorch forward pass. We got to write a ReLU. What is it? Max 0x. Or np dot. Yeah, that's right, isn't it? Oh, is it max? Yeah, it's max. NumPy's not picky about its types. What? See, that's what I mean. I'm not sure. The shapes are not aligned. Yeah, see, I don't like that. I'm confused by why PyTorch has their matrices like that way. Isn't it really like that? What do I want to say? Transpose? Only integer scalar arrays can be converted to a scalar index. Okay, good. We got some. It's not the right shape. I didn't even get the right shape out. let's not make the batch size 10. Let's make the batch size 32. Okay, we got 32 times 128. Now the batch should still be the same here. What? Oh, that's not what max is. Oh my god. My ReLU was broken. We gotta do maximum. Let's just make sure that actually does what I want. Just do a batch size of 1 for now. Does my ReLU work? Did I write a crappy ReLU? Wow, that's a lot of zeros. You know what they call that? ReLU death. Because you know what the gradient is with 0? It's 0. Okay, so that now, what do I want to do? We can just say, y test preds equals np.argmax. Dim equals 1. No, see, in PyTorch it's dim, and in NumPy it's access. Why do they call them different things? That's mean of them. All right, let's go. Speaking of mean, that one. All right, good. Well, look, we get the same results in NumPy as we do in PyTorch. How unbelievable is that, boys? That's unbelievable. All right. But we're not really going to copy the weights from PyTorch. Now we're ready for the real challenge. Training in NumPy. Because we wrote test in NumPy, we still got to write training in NumPy because we didn't do that yet. Let's check in on chat and see how you guys are doing. Also, we're not plugged into the wall here. So my laptop's going to die, and then there's going to be no more streaming. You're all going to be sad. And that's why I like, my laptop loves European stuff. It's European power. It loves European power.
I bought that map in Europe.
Yeah, it looks European. No, my laptop loves European stuff. Don't worry. Build autograd. Ooh, build autograd. Now that's for real, like Giga Chad mode there. I don't know. No, I know Vim today. Is this my mom's basement? Mm-hmm. Is that a piggy bank? Mm-hmm. That's the most realistic looking pig I've ever seen.
They cast a real pig. It's a dead pig and they cast it and it's a real pig.
Is there pig inside of that?
No, it's money. One day we're going to take the pig somewhere and buy dinner.
We're programming the matrix. We did do some matrices. You got to know how to multiply matrices. Yo, should we do it without NumPy? Should we make this work without NumPy? Should we program matrix multiplication?
Robot left me all this change.
Are we allowed to just use np.dot like savages, or should we program our matrix multiplication so we get the axes correct? Do you guys know how to multiply a matrix? NumPy is cheating, bro. But not with default Python lists. I mean, np.dot is a little bit cheating. Do it with Python. Oh, now it's going to be slow. Why don't we just code it in C while we're at it? Please don't use Python what? Oh, yeah, check out my American flag spatula. What? Alex, everything I have is here. I brought you clothes today. What am I going to do? Go cook at my crack den? What's Kona? Do it with eigen. Oh, yeah, that's C++, you know? What's K Kona? No, we're gonna write K Kona means American. I don't know if I believe that. Are you guys giving me some memes that'll get me banned from Twitch? All right. It's an emote for America. All right, we do love America on this channel. We do love America. All right, well, you know, I'm real scared of getting banned. You know, they're coming for, you know, first they came for the white supremacists, and I didn't speak out because I wasn't a white supremacist. And then they came for Hunter Biden, and I didn't speak out because I wasn't Hunter Biden. And then they came for me, but there was no one left to speak out for me, guys. You know, when the censorship comes, listen. When the censorship comes and nobody can speak freely, Fairbanks, Alaska. Let's just go. Let's just go. Let's everybody go to Fairbanks, Alaska, and I want everybody to remember that. You know, when everything is dead and there's no hope left in the world, the Schelling point is Fairbanks, Alaska. And we'll all just descend on that place, and yeah. All right. When they come for us. Might sound weird. Yeah, they're trying to censor Fairbanks, Alaska, but don't worry. The message is getting through. Nothing left on Twitch when white supremacists and Hunter Biden are gone. Ooh, f.relu. Oh, that looks so much nicer than having to like put a relu there. Oh, let's upgrade BobNet with an f.relu. Oh, f.relu. Oh, that's so much nicer than nn.relu. It seems fast, don't you think? Look, it's lowercase. That means fast. What does the F stand for? Fast. Oh, look at that. We even got pretty much the same accuracy with F. Okay. No, I'm procrastinating now because, to be honest, I don't really know how to do this. All right. We got to compute derivatives. There's probably tutorials, but we're going to try to figure this out without a tutorial. Oh God, this is hard mode. This is hard mode. No, we're going to need a tutorial. I don't know how to do this stuff. What's the chain rule again? I don't know. I don't remember. We gotta like get derivatives of logs and shit. This is too hard. The loss can be described as minus x subclass in the case of the weight argument being specified. Super hard. Okay. Oh, I know. This is called a log x sum. Let's just break this up a little bit. So I can do like np.x.sum. I'll take the log of that. X subclass. Whoa, no way. It's like the same. It like knows it's 7. That's pretty good. Ooh, we can, yeah, look, we can compute uncertainty. see. How uncertain? Is that uncertainty? Well, let's see if I can write this for so it works for multiple. Just gonna have to change sum to be axis equals 1. Oh, the European power is shocking my hands. You know the converter doesn't do anything, that was just a wire.
Yeah, the lamp has a European bug on the end.
Yeah, it's just a wire. It doesn't do anything. It is shocking my hand, though. Can I write that? Is that right? That's not what I want. That is definitely not what I want. How do I write this? No. That's how you write it in Torch. No, that is not what I want. I want to like select it for each. Do you see what I'm saying? That's that. And then for each one, I want to select. Is this not obvious how to do? Like, so we have y-test, and y-test has shape, you know, that. We want to select for each one of those. That's not right. How do I do that? You see what I'm trying to do? Let's see if chat can be useful. Bro, you need to get your cost function, which is the func of output, which is the func of your net params, and then differentiate, bro. You got 2 I's in differentiate. I'm in the cloud. Y'all know that. You guys paying attention? How many people are watching right now? I don't have that up. Like, how come that's not an easy operation in NumPy? I really don't understand how to do that. It's called like NumPy gather? Take. Oh, wow. How have I never used take before? That's not what I want. No. NP take. It's not what I want still. What I really want is like this. For I in range, y-test spreads out, dot shape, sub 0. And I want to say this. Or I'll just write it in this notation. Y-test spreads out, sub I. Y-test sub I. I want to say that. What? This does not already bode well if I can't do that. Oh, I guess I could like encode it to 1 hot and do it like that. Who invented logs and shit? 714, 700. Oh, that's how many people we got watching. Y-test spreads out. Oh, you're right. It is that. Thank you, Otor0. You're a bro. I have seen this before. But Yeah, I've seen this before. It's that, and that's so stupid. Because, you know, I don't want a range there. I want to write that, but why is that a different thing? All right, cool. That's a nice measure of uncertainty. You want to figure out what the highest uncertainty is? Let's take a look. Let's say np.maxrat. No, np.argmaxrat, yeah. So let's take a look at this image. Who's going to be confused by it? xtestrat. Arrays used as indices. Oh, God, sorry. Yeah, see, what number is that? Nobody knows. Nobody has any idea. I mean, it's probably a 6, but really, nobody knows. See how confusing it is? I'm confused too. I am just like network. Network and me are the same. Guys, if you don't understand this, we're not even up to the hard stuff yet. We've been doing easy stuff. We've been playing on easy mode. We've literally been playing MNIST classifier 101 shit. Looks like a crippled 6. Yeah, that's right. Let's see, what else is confusing? What do I want to do? Let's zip ret range ret.shape 0. Let's do this. Sorted list. I know this is the content you like. I know this is the content you like that you're here for. We're working hard to make content that people like. Oh, let's look at more messed up images. Oh, yeah, I don't even know. What is that? What is that? Oh, that image is so messed up. But if we set reverse to false, let's see what the least messed up images are. 13. Let's see. Oh, yeah, everyone knows what number that is. Wow, that number is so obvious. Oh, let's look at 69. Oh, yeah, wow, it's really good at zeros. Is this one a 0 too? Oh, that's an obvious 3. That is a beautiful. That is a canonical example of a 3. If Michelangelo sculpted a 3 instead of David, he would have sculpted that 3. This is a beautiful 3. Let's look at more messed up numbers. Is this the content you want? Yeah, we're looking at messed. Oh, yeah. Oh, 6s are really ugly. 6s are like yeah, they're spermic. You know, it's like phallic, but ugh. 2? No, that's not a 2. You think that's a 2? Maybe. It's a weak 9. So weak 9. You think it's a 7? That's artistic 7. I hate when people try to be artistic when they're drawing 7. Oh, look at that artistic 2. Got a little swoop in there. Plot them all in a grid. Oh, you guys want me to write a grid? All right, let's go. What do you want? A 4x4 grid? Grid. You know, am I really writing a grid for you guys? Oh, what's the easiest way to write a grid? I don't know a good way to do this. Who wants to write a grid on easy mode? xbad.reshape 4, 28 times 4, 28. And now we just say np.concatenate. I concatenate on axis 2, but is that going to be the shape I want? Out of bounds of array of dimension 2. Oh, that? Yeah. All right, let's see. Did my magical grid code work? Oh, that was the most beautiful grid code I've ever written. Oh. All right, let's make a parameter called g for my grid. G equals 4. Call this g times g. Put some g's in there. Got a g up in there too. Oh, that's the most concise, beautiful grid code I've ever written. Oh, that's beautiful. No, but actually, let's look at beautiful numbers. Let's really look at like the pinnacle of number. Oh, these are the pinnacle. That 4 is kind of ugly. You know, I thought that was supposed to be the pinnacle of number. Let's make G big. Yo, let's make G 8. That's a big number. Yo, that's a big G. What? How does it know what number that is? That's the most confusing ass number I've ever seen. Let's look at really confusing numbers though. Oh, these numbers are gross. Oh, by the way, is that not the most beautiful grid code you've ever seen? I mean, I've written that coded comma as like a big function, and then I'm just like np.concat reshape. That's right. That's how you write a grid. All right, so who knows how to differentiate this? How am I going to differentiate log x shit? I don't even know how to differentiate a matrix. We only look at pretty numbers here. Let's go 16. Oh, it's crazy. Like the computation power that lets me, yo, let's go 32. Wow, the computation power that just lets me do that. I love the future. I love the future. I just want you, like ENIAC fuckers, you know, like ENIAC fuckers who were like, oh, well, I have to make sure there's no bugs in the vacuum tubes. And I just did that. I just made a grid, 32 by 32. 32 times 32 is such a big number that I didn't need a calculator to do it. Is it 496? It's 1024. Wow, see, I don't even know. Yeah, well, it's 2 to the 5th, and 5 plus 5 is 10. 10 to the 2 to the 10th is 1024. I should have known that. I should have thought before I spoke. Oh, that's beautiful. That's just okay. All right. We're getting distracted. See, I have chat open and I'm distracted. Okay. We are going to make it train in NumPy. I believe in us. We're going to finally figure out how to differentiate a log exp. I don't even know. I mean, I can have PyTorch print the gradients and we can check if they're right. No, I'm closing chat, Peak Strip 1. Maybe if you were a subscriber, I'd care about your opinion. All right. Whoa, np.gradient. You're a VIP, so I believe in you. Wait, can I actually do this? Yo, let's go. np.gradient. Well, actually, I do want to add this to the forward pass. Well, we'll add the log exp to the forward pass. That's not even, I can't even do that. All I can add to the forward pass really is the exp. Differentiate by hand and write the function, bro. You know, not all of us went to school, okay? This is np.gradient. See, that's my school. All right, let's go. Does this work? Oh. Turn the gradient of an n-dimensional array? I can't just do that. Wait, that just takes the average or some shit. But you're a VIP, so I believe in you. Oh. The gradient of an n-dimensional array. Oh, it's change in y divided by change in x, so it's divided by... So this one they divided by 1, and this one they divided... I don't get it. I don't think that's right. I don't know. Okay. we're gonna use Google. In this section, we will develop expertise with an intuitive understanding of backpropagation, which is a way of computing gradients of expressions through recursive application of the chain rule. Understanding of this process and its subtleties is critical for you to understand. And you think I should understand it, but I don't. I'm a neural network script kiddie. We're going to read. Slow mode read. All right, let's go. Recall that the primary reason is this written by Mr. Karpathy himself? Recall that the primary reason we're interested in this problem is neural networks. F will correspond to the loss function. Let's start simple so we can, yeah. So I believe we're trying to compute the gradient with respect to the input. That looks really hard. Yo, you know what? Why am I using dot transpose when I can use dot T? Oh, that's so much nicer. All right, let's first look at the gradients in PyTorch. Let's use PyTorch as a teacher. I mean, I have done this stuff once in my life, but like, I don't know it off the top of my head, and I should, if I want to really be good at neural networks. Yo, I bet there's people like who know off the top of their head what the first test image in MNIST, what number it is. Is it a 7? It's a 7. Oh, that's a beautiful 7. You know what? I made the fig size too big, so that my 7 was too big. Oh yeah, tiny fig. One D target tensor expected, multi-target not supported. Oh, because it's y-test. Okay. All right, so can I say like loss.grad? It's not a leaf tensor. Use retain grad. So I don't understand why it's not a leaf tensor. There's probably ways to like view the graph. Oh, and then before we do backwards, I forgot to do optim 0 grad. That's in the optimizer. I can say model.0 grad as well. I think that makes more sense. But I really forgot to do that in one of my things, and that's why the learning rate was so high, and I couldn't get my examples to work well. I mean, I had to set the learning rate so low. Okay. Okay, so we zero the grad, we compute the model, we compute the loss function, and now we check that. So now can I say like model L1 grad? Linear object has no grad. Await dot grad? Wait, it can't be 0. It can't be that perfect, can it? It's 0 up there, but it's not 0 everywhere. Okay, that looks quality. Oh, can I do out.grad? Grad attribute won't be retained during autograd backwards. If I want it, it's not a leaf tensor because it's only used in other computations. Can I do that? There we go. Okay, so this is the gradient with respect to loss.grad is 1. Why is it 1? Oh, there's also a mean. There's like an implicit mean in there. Let's get rid of that implicit mean. We can do it with a reduction. What if I say reduction equals none? And then shape is this. $128. Okay, so that's for the batch size. That makes sense. Oh, yes, it's slightly better. Okay. I don't get... What? Oh, that's 1. Okay, that's fine. Because there's only one example there. If I did 2 examples... Grad can implicitly only be created for scalar. What? Okay, let's see if we can compute this, which is the gradient through the loss function, which I think is what we have to get right first. Ugh, it's just ugly. I hate when it gives errors like that. Okay. Backward pass cross entropy loss. Well, we can break this up a little bit more. We can write log softmax, right? And NLL loss is a different thing. All right, let's add if we use normal softmax, then what's the loss function? Use log softmax. And then instead of doing cross entropy loss, we'll use NLL loss. Implicit dimension choice for log softmax has been deprecated. Oh, name equals 1. Whoa. Maybe we should pick a more controversial sample. Is that really right? That it's just -1 there? Can be described as I guess that's kind of right. Yeah, it's still -1 even when I reinitialized BobNet. Well, that's a simple enough loss function. I do know how to take that gradient. What if I say model.sm.grad? Log softmax object has no attribute grad. Oh, because the weight would have to be the gradient. So it has a gradient, it's just that tensor is created implicitly. There's ways to like debug autograd in this stuff, isn't there? Okay, well, either way, that's easy enough to compute, which I like. So it's just 7, right? 0, 1, 2, 3, 4, 5, 6, 7. So -1, and then we have to put it through log softmax. What's the derivative of that? You know, we don't have to use a model here either. This is using a lot of fancy torch stuff we don't have to use. We can kind of meet in the middle. Like if I just made those normal matrices. And for that, I can just run that. Let's check in on chat. Bro, just use Wolfram to get the derivative, bro. You know what? By Chid69, that is not a bad idea. Let's just get the derivative of this thing. Wolfram alpha. So I want the derivative of log softmax. Okay. So log x divided by, sigma. Let's just say x plus x y. It's not a vector. Assuming log is the natural logarithm. That is exactly what we want. Derivative. See, I'm not even really sure what that means, because I can get the partial derivative with respect to x or with respect to y, but I really want the... Okay, let's first figure out what I'm trying to do. I'm trying to get the derivative of the output with the input with respect to the output. All right, so first let's start with np.zeros 10. Then we say out sub 7 equals minus 1. Okay, look, that one looks the same as that one. Oh, I did it so well. All right. Now, derivative of log softmax. Want to get food? What are you doing over there? Oh. Oh, yeah, what happened to IKEA? I have an idea. Why don't we read the PyTorch source code? You don't know if there's enough food for me? This function doesn't work directly with NLL logs, which expects the log to be computed between the softmax and itself. I mean, so I should be able to, let's use a little PyTorch for a second. So if I do, where is that defined? Torch nn dot, let's say g in. Wait, no, that's the gradient in. That's not the, in fact, I can just say like L2 sub 0. So it's that I want to take the softmax of. Well, no, not L2, just X actually. Well, X test preds it out. Yeah, that. Let's retrain the model quickly. All right, I think what we're going to do is we're going to get lunch, and then we're going to come back, and then we're going to solve this. Hopefully it's all set up. Got it beautifully set up. I can push this to GitHub if you guys are interested in playing along at home.
Let me get dressed.
What? Let's take a break for a minute. Half done MNIST from scratch. Promise I will finish soon. All right, you guys can play along at home. Just so you know what we are trying to do. Is it clear to everybody what we're trying to do? We're trying to re-implement that backward pass. I mean, the forward pass was so easy. We already got the forward pass done. We're trying to re-implement the backward pass in Numpy, and then we're going to train this exact same network in Numpy. But we have to figure out how to get the derivative of log softmax. You know, this is complex math, but we're going to be able to do it when we come back after lunch. I will see you all soon. Thank you for subscribing. Symbolab. Oh, log of softmax derivative on math stack exchange. I was reading about the stack exchange controversy last night. It was some Monica girl. We are all Monica. No, they Monica, man. Everyone's protesting. I hear Stack Exchange is horrible to their users because they didn't reinstate Monica. I stand with Monica, I think. I'm not really sure. From the 2 minutes I spent reading about this last night. Wait, what's the lavender letter? Wow. No. We're not going here. Log of softmax function derivative. Using the log identity. See this stuff. Wow. That's why you never go on math stack exchange. Compute stack exchange would give you codes. Cool. Yeah. We'll be back from lunch in like I don't know, like an hour or something. Maybe. 80% chance. All right. Thank you for watching part 1. We'll be back for part 2 soon. No, we never back down when there's a challenge. Never give up. Never surrender. We got some caffeine food. You got any caffeine food or just lemon bitter?
I have oat milk latte and I have tea. You want tea?
Yeah, tea sounds
Like
nice.
some caffeine?
Yeah, with some caffeine and lemon spindrift. Lemon spindrift, let's go.
Wait, bring your mug back.
Bring my mug back, okay. We're gonna cook. And by we, I mean, well, not we. And we're gonna have tortellini, and we're gonna have salsa. Do we have chips?
Yeah, of course.
Oh, we got chips too, and no sour cream. This is disgusting food.
I agree.
Yeah, oh, this sounds so lovely. My days are so lovely. Welcome to Sunday. Saturday. It's Saturday. All right. We're going to conquer these derivatives right now. We gave up when it gets hard, and if we give up when things get hard, what example would we be setting for the children? A bad one. That's right. Set a good example for the children. Let's go. Okay. Let's first do this in PyTorch. Torch.tensor that. Torch and then log softmax of gin. Jout. Functional. Gotta put dim equals 0. Let's print gout. Okay. Those are big numbers. Ugh, I hate when torch, no scientific notation.
Sorry,
Whose sound?
I'm sorry
Oh no, they love sound. Who likes scientific notation? Who made that like the default? Oh, my grid is ruined. I can't call things grid. Oh, those are much more reasonable looking numbers. What do y'all think? Now we have out. I feel like I can't do the backwards pass yet. Okay, so that's what we got from log softmax. Oh, that's good. That like makes sense, right? Because it's so sure that it's a 7. What is it so sure about on this one? This one, it's almost so sure it's a 3. We should probably do this too, just for politeness. Okay. No, we don't need politeness. No, let's go. So now we have like this, and like that's the derivative? I guess that's the derivative. That's not the target. What is NLL loss? Let's just read what NLL loss is. NLL loss. With reduction set to none, it's this. So weight. Oh, I guess the loss is just like selecting it. So if we just actually, it's this vector. So we can say something like loss equals gout.
Are you making it a little spicy?
How are you making it spicy?
They substituted me on hot salsa. So.
Oh yeah. I love spicy. Wow. Torch 1264. Let's just actually put this up here. All right, and then here we can take the mean, so we have no loss there. Doesn't seem right. That one has loss? No, like, no. I'm forgetting a negative sign somewhere. Oh, there's my negative sign that I'm forgetting. So the negative sign goes in front of the weight, which is that. Thank you. Does that like match what we're seeing for the loss? Yes, it does. So if we just do this one, yeah, this one has no loss. And that one has big loss. That one has less loss. Okay, good. Now if I do loss.backward, does that work? Element 0 of tensor does not have require grad. Sour cream is disgusting. It's not. This isn't a debate that I'd like to have on stream, but I believe.
You're afraid to show people who you really are?
No, never. I would happily tell them that I think sour cream is absolutely disgusting, but I haven't really rehearsed my debate yet. And you know, everything I do on the stream, I practice it before I do it on stream. Right, tensor got an unexpected keyword argument, retain grad. Why can't I retain grad? Oh, maybe I just do gin.retain grad? Oh, dot retain grad, not retain grad equals true. Yeah, because we want to retain grads. That's right. Cannot retain grad on a tensor that has, requires grad. Okay, we got to require the grad. All right, we did loss.backwards, and now we can do gn.grad. Oh, well, okay, that one doesn't really have any loss, so that one's kind of unfair. But if we do this one, it'll have some loss. Okay, good. Okay. So, yeah, I think that's our output. dsm equals gen.grad. Yeah, look, we took the derivative. Yeah, who likes our answer? Okay, that's pretty good. Let's just do the same one here. Yeah, now let's see if we can get the same answer. Okay, the other derivative should be easier. I think that was the hardest one, and we did it by cheating. Oh, I know why the loss is so high, because the answer is not actually 7. Yeah, now the loss ain't so high anymore, eh? That one still has loss. Let's just check here if this has loss. No, that one doesn't have loss, but this one does. That's a good amount of loss. You guys want to take a look at it, just so we see like what we're looking at here? It's a 2. Let's confirm that it's a 2. Oh, we can't show it. It's a 2. Oh, okay. So the derivative says make it more 2 and less 3, I believe? Or more 3 and less 2? I don't know. This doesn't make any sense. Less 3, more 2. Okay, lesson learned. And then we want things that look like this. We actually can't get that derivative there. Oh, but actually, I think I can say, not requires grad, but this one's going to complain. It's going to say that you didn't retain the grad, and you need to retain your grads. But just to confirm that this is going to be that, but minus 1. What do you mean, what am I doing? Oh, they love when I explain what I'm doing. What am I doing right now? Yeah, well, do you know what MNIST is? Do you know what MNIST is? No. MNIST is numbers, and you can get the computer to tell you which number a number is.
Oh, the computer tells you which number a number is?
Yeah, it's pretty good at it too. Like, you want to see some numbers?
Oh yeah, I'll look at it.
I'll show you some numbers, and then the computer can tell you which number it is using matrices. You know, because we love matrices.
That's correct.
Yeah, but getting the matrices to be good at telling you which number numbers are is that what we're trying to do, and it involves calculus, and I'm not very good at calculus. I'm good at programming, but I'm not good at calculus. So we're cheating, and we're using programming instead of calculus, and it's sad. We shouldn't be doing that. We should figure out how to compute that without it. But we'll get back to that one. I promise we'll go back to that one. Let's move on now to L2. We got to get the derivative of L2. L2, yeah, so this one's just like we're going to like transpose the matrix or something. Number rectangles go burr. See, and now it's, yeah, okay. So we should be able to produce the same image using Numpy. Is it really just, you know, let's just try some like dimensional analysis crap. What if I just do L2.t? Is that the same image? Oh, invalid size. Oh, it's only an invalid size because we should really do, yeah. Let's make everything batch, because if we don't make it batch, we're going to regret it later. How did that break? Oh, because dim equals 1. Remember when I wanted to make dim equal 1, and you guys were like, don't make dim equals 1? That's a lie. You guys are just controlled opposition. dsm.shape, l2.shape. I don't even think I have the shapes right. Oh, because I used 10 there. No, I didn't use 10. It just is 10. Yeah, okay. So we just don't understand what we're doing. Let's read backprop. It tells you how to do it with a matrix. Weight.t.transpose.dd. Tips, use dimensional analysis. Oh, good. That's what I'm good at. Sweet. Okay. What is x? Oh. Okay, so we're doing the forward pass where we're doing w.x. Should I not have transposed those? w.x, x.that. That seems right. Probably the most tricky operation is the matrix-matrix multiplication. If we want dw, suppose we have the gradient on D from above in the circuit. Okay. So we do have the gradient on D, which is DSM. So we want to say DSM dot, I think it's L2 dot T, and I think that is the derivative. Because I think like dw is that, but it doesn't have the right. Shape. Well, so if that's dw, like somehow that became. Okay, so I guess first we compute. Well, so this isn't dw. This is d. Oh, yeah, no shit. We have to retain the things from the forward pass, yo. If we didn't do that, of course it doesn't work. Yeah, what am I trying to do? We didn't retain the thing from the forward pass. I'm trying to compute this without actually using the image. Okay, we got to name things more carefully. So we're going to say x underscore L1. What do they name things? You know what? We'll just say, yeah, x underscore L1 x equals x test 2, and this is going to be x dot L1, which is x dot L1, x relu equals np maximum xl1 0, xl2 equals x relu dot L1. Yeah, so it's really this that we have to compute. This isn't L1, this is that. Wait. Alright, let's just print the shapes here.
Alright, there's two different kinds of chips.
Thank you. Oh, this looks so good, Alex. There's cheese?
Yeah, it is so good.
Mm. That's delicious. Thank you. Oh, and then actually we can confirm that these are the same things. Like it has to be, right? Yeah, they're the same. Well, but they're not actually perfectly identical. They're very close, but they're not perfectly identical. Okay. So then here we can just make this XL2. All right, so what was the input? We want x relu. And then actually, I think we want let's just try that. No. So, in this example, our W is x relu, and our L2 is x. So we want to compute DL2, and DL2 equals L2 dot transpose dot DSM. That's not right. Same shape as D. It is the same shape as D. Oh, did you make your own?
What?
Did you make your own?
Yeah.
Oh, the sour cream? I don't know how you eat that.
What?
I don't know how you eat that. What am I doing wrong? You guys like screaming it in the chat? Chat is quiet today.
Spicy.
Too spicy?
Hot salsa stuff.
Mmm. Okay. So, in our forward pass, let's just be explicit. W is XRELU and X is L2. Our XRELU has shape 1, 128 and L2 has shape. We're trying to get the derivative of x, so we're trying to get dx. So we can do XRELU. Oh, is that just right? Yeah, okay, that's right. Perfect. Is that the same image? I mean, we can transpose it, but. Okay, good. Look, that image looks the same as that image computed by PyTorch. Oh yeah, we're making progress. We made our first derivative. We also need dxRELU. Should go on to the next, because we're going to need that for, oh, now what's the derivative of a ReLU? You know what? This one, I think I can figure out. No, actually I can't. What's the derivative of x? It's just 1. And then the derivative of 0. Wait. Is the derivative of a ReLU really just that, that, and that? I think that's right. So it's just 1. Wow. Is that really the derivative? No. Huh. I mean, that seems right, right? Mm. How?
What? You want a napkin? You just left the bag, but you take it.
They're not looking.
Can you remove that part?
What? No, nothing can be removed. Everything on the internet is forever. Ask Hunter Biden, he knows.
Oh, man. Ask anyone if they can do a computer repair shop.
We were trying to figure out what news is fake and what news is real. It really does seem like the derivative of ReLU is just 0 if x is negative, and when one of x is positive. But that just seems too simple. I mean, let's try it. Derivative of ReLU. So we're trying to figure out what dxL1 is. And then according to that, it would just basically be this. Maybe. Let's name this better. dxSM. Name this DL2. The derivative of L1, if that's x ReLU, then I think that's just x dot dxL1. Does that image match? Almost. I think my ReLU derivative is probably aggressive. It's probably not right. Because that doesn't look like that other image. Thank you. We got tortellinis. Yeah, it's good to me. Yeah, that doesn't look right. Great, the one derivative that I calculated myself is wrong. No. Okay, that says right. Wow, is that really the derivative of ReLU? That's unbelievable if that's true. Okay. But no, that doesn't explain why my image doesn't look like the other image. So x ReLU is what's going into L2, and x is what's going into L1. So that dot that. That's an L, not a 1. What'd I do wrong? Probably. No, I probably got one tiny thing wrong. I'm a little shocked that the derivative of ReLU is that. I probably have to like multiply it by something for the chain rule. Just remove bro, no differentiation. ReLU is not a continuous function. It can't be differentiated. Yeah, nobody cares about that. I probably have to multiply it by something for the chain rule. After all the good comments, you read my crap. Backprop for ReLU is you take the dx coming backward and zero out the entries that had negative pre-activation. Is that really right? So you're telling me it's this. I mean, this seems more right to me. I'm not exactly sure why it's true. That still doesn't look right. 'Cause I guess, I mean, we have to use the chain rule. Pretty sure Relu evolves into Lucario. I know Torch does the chain rule for me. 1 if x greater than 0, else 0. But that's exactly what I wrote here. Like, I just can't believe it's so harsh. Okay, so I guess I do have to, I probably have to multiply it by the input then. Because that's the chain rule. That still doesn't look like that. All right, let's look up the chain rule. Did you want to look at the numbers? And the computer will tell you what those numbers are.
Oh, that's cool.
Yeah, like reads numbers. This is like the classic machine learning.
I've seen this before.
Yeah, it's famous.
Why are you doing it?
What? Did you just ask the why question? Oh,
Who made it?
Mr. Jan LeCun.
Oh, geez. Isn't that guy too lame now?
Jan LeCun? No, Jan LeCun's not lame.
Oh, that's right.
His feud with Schmidhuber is lame.
I don't know about the food.
No, Jan LeCun, I don't know. I mean, I guess I was a big Schmidhuber fan, but then, like, what does Schmidhuber do today? He still complains about the feud. There was, like, a feud, and there was, like, leaked videos on YouTube of, like, you know, him, like looking at Jan. It was weird. No, the feud had to do with, like, who invented deep learning. It was stupid.
Who invented deep learning?
Who cares? I think Andre Karpathy did, actually. That's what I'm going to go with. Okay. Then the derivative of, if we define, yeah, so this kind of seems like why we do have to multiply it by dx ReLU. So that's probably right. Why doesn't my picture look like that picture? Too much food? Oh, wait. No, I think one of these shouldn't be dx ReLU. One of them should be x ReLU. Yeah, there we go. Boom. We used the chain rule and we figured it out. Is that right? Yeah, so we just zero out the derivative everywhere. We zero out the derivative everywhere that the original function was negative. Okay, and now we're done. Now we implement the learning rule. Oh. No, we have to do the derivative of log softmax. That isn't done like that. The sauce is spicy. You told me 10 minutes ago. Yeah. I'm sure you told me 10 minutes ago. Okay. Can't use MSE for classification, bro. That's exactly. Bitchid 69 knows what's up. So therefore, we have to figure out how to get the derivative of log softmax. Okay, well, so we know it's going to involve, will involve XL2 out. I'm going to move this down back here. Will involve XL2 out and produce DXSM. The derivative of log softmax equals one minus softmax. Minus softmax if it's not equal. First note that that's what softmax is. So if we want the derivative, oh my god, see, look at all these upside down. Why do they use symbols in math? Why can't they just use normal people things like letters? All right, that's the softmax function. Cross entropy with softmax. Oh, this looks nice. Oh, now that I turned off scientific, what? Wait. Oh, I didn't turn off scientific notation for Numpy. That one I actually know how to do. getting these Z's and Y's and K's from. Is just equal oh. Time of the forward pass, you have that. Okay, grad input, one. So I don't really know what the grad output I is. I think it might just be that, but negative. Well, let's just first try. It looks like we're doing an exp on the output. So if those are the three things, that's the input. Those are really large numbers. Is that really right? Nans. Even worse. We hate nans. Exp output. Sum minus exp times sum. Grad output data. Okay, so softmax is that. This code doesn't look very competent. Because this is it's gonna set this over and over again. Okay, let's go back to first just computing the log softmax, which we were doing, whatever that range thing was. Here. So that's wait, if I set softmax, let's just use softmax, forget log softmax. Just want to know how to turn that and that into that. Log softmax update output. TH tensor new contiguous grad output. Grad input equals grad output minus x times sum. So first we sum up the grad output data, which I actually think is just -1. Those numbers are just crazy small. Oh, probably it's related to... Yeah. Oh, okay. I think I get this. All right, so we're going to need the sum. What I just don't understand is how it's not the sum of the x's. Oh, I guess that is output data. Yeah, okay. So first we have to get the output data. We haven't actually computed the forward pass. We haven't computed x underscore sm yet. So how can I expect to take the gradient? So we can do the forward pass on softmax. I made that same mistake twice. I forgot my forward pass. So the forward, where do I compute that? Again, it's that range crap that I did. Here we go, this. And I called it big stupid things. I feel like I just did that already. Okay. XSM equals minus XL2 oh, we need out here. Times out plus np.log np.x xl2.sum. Axis equals 1. Oh, that looks similar to that. I think you're supposed to do a stability hack for softmax, but I don't really care. No, it's like not really times out. Maybe it is. Okay. So we have that. Those numbers look suspiciously close. So that's output. Take the X of the output data. Really big numbers. Oh, actually, let's rename this to LSM because it's log softmax. So, to be right, if I go like that, does that give me like reasonable probabilities? No. Well, actually, this should be the same thing as GL, right? Am I not even getting the forward pass right? Yeah, I'm not getting the forward pass right. Okay. Because there's a negative that I'm forgetting somewhere. The log softmax function. This like simplifies to something though. It's like this in theory, but like you can simplify this, right? So in log space, that's just the same as dividing is the same as subtracting. So we can just do some 2 there. If I want, I can just take that outside and I can do np.log that minus log that. Why is that not right? Oh, well, that didn't compute it for each one, and that computes it for each one. So times out. Negative infinities. Oh, I didn't do an exp. Oh, but okay, log of exp is just the same thing. So, yeah. It's that, right? I mean, they're similar. I feel like that's just due to numerical instabilities in here. Log exp sum? Is that a NumPy function? Yeah, but that's probably just numerical instabilities. Okay. So that's the forward pass of the softmax. I mean, okay, that's actually a lot to attribute to numerical instabilities. I don't think it's numerical instabilities. Because out's not right. Oh, I have to compute it for like each one. What if I do that? Oh, there we go. Okay. Don't attribute to numerical instability until you've tried harder. Good. Okay. So this is a log softmax forward pass and it matches. Let's clean up some of this crap. We don't need that anymore. All right, now we're actually finally doing the forward pass. Those two things match. Now we have to figure out how to get the derivative. Okay. That shouldn't have anything to do with out. Yeah, so the log is just this, so we have to take the derivative of that. Oh, wow, okay, I was being a noob. I was trying to combine the things together. Don't do that. All right, so that's the derivative of out. I'm not exactly sure how it got that. Oh, because the mean is the derivative. I get it. D out equals negative out divided by 10. So those should be the same. Okay, those two are the same. All right, now let's see if we can produce that. And now we can go back to that code and we can look at what it's doing. Okay, so we want the sum of the grad output data. So the grad output data is D out. So we can say dout.sum is sum. And then the output data itself No, I don't think that's right. It's not out, is it? It's the grad output data. I guess that output data is the output data from log softmax, which is x. Let's exp that and see if it looks reasonable. Okay, okay. So what if we just, is it this? D out equals np exp lsm times d out dot sum. Just call it alt for now. D out minus. Oh yeah, buddy. dx lsm equals d out minus np exp lsm. Gotta cite my shit. All right, now we have dx lsm computed from that, and the pictures look the same. Yeah, buddy. All right. You know, I kind of want to keep that PyTorch code around. Let's not delete it. Nah, we don't need this PyTorch code. We just want people to think we're pros, and we didn't need it. So actually, to be complete, we can say x loss equals x LSM negative out times x LSM dot mean dim1 axis equals 1. So that's the loss. Now if we want dx loss, which is that. Do we actually have to use x loss anywhere? I feel like we should, but yet I don't. What do I call it up there? Samps? Samp. It should work for 2 samples too, right? I don't know why it doesn't work for 2 samples, but we'll deal with that later. Okay, forward, backward pass. Okay, we have the gradients now, the weight matrices written entirely in what is x loss? Oh, I'm not even setting D out anywhere. We have to set D out. That's probably why having two samples didn't work. No, it's not why. All right, let's go through. Test subsamp, x dot L1, NP maximum. Delete that, delete that. Let's see if it works for a different one. Actually, let's use the same code. Just say samp equals 1, samp there. So what if I do 1, 2 there? It does not work. Greg can only be implicitly created for scalar outputs. Oh, because we have to take the mean. I don't really understand how to do that. That's going to be a nightmare. Because there's only one weight gradient and it like computes it over the mean. Okay, well, you know, we can just compute the gradients one at a time. It shall be slow, but you know what they say about slow? It's okay. Great, it's just okay, okay. Do those two pictures look the same? They don't, huh? What did I not do right? Oh, I should have left that PyTorch code around and we could have compared them. Yeah, my x1 gradients totally don't look the same. Let's just hope I made a typo. DXLSM, T2, XRELU. You know what? I know how to check for a typo. Restart and clear output. Train the PyTorch. That's the gradients at 0. Copy the network. NumPy forward pass. Confirm they're equal. DXSM. Aha! DXSM, because that should be LSM. My DXRELU was wrong, and that's why my pictures didn't match. Beautiful. Junk. Junk, 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 junk. Let's commit this. We have NumPy backwards pass. No, what? What's wrong? You can tell me in the streamer. You can tell us? The board over there. I'll be right back, streamers. Oh, machines. Computer hours. glitchies, I know you're still there. I see you. Can you see me? Glitchies see a lot of things. Hi, glitchies. Oh, we're tiny. How many pixels do you think we are? Yeah, the progression algorithm is pretty good, but the rest of the image is so still. You want me? Should we stop? Should we stop for the day? I promised Alex today we were going to smoke weed and watch The Sopranos, and instead, you guys all got a shitty calculus lesson. How many people we got watching this? You can always see me. Oh, they can't see shit. Yeah, they can't see over there. Better calc lesson than I had in college. Yeah, we struggle until we get the derivative to match torch. Yo, imagine the first guy who had to figure this out and couldn't just compare it to torch. Man, that's the Lewis and Clark of deep learning. Ooh, Carpathy wrote an autodiff. Ooh, we could do that. Nah. Newton just wrote it on paper. Newton couldn't import torch. Shit, man. Imagine you let Newton import torch for a week. Yeah, I'm lost without test vectors, too. What? Oh, you want me to use the big handle? Wow, I feel like Newton. I bet Newton had some shit that looked like this. Alright, let's go to the bathroom and then let's get back to work. We still got to implement the fun stuff like gradient descent and Xavier initialization. That stuff's fun. You know what wasn't fun? The derivative of log softmax. And the derivative of ReLU was shameful that I didn't know that. But the derivative of log softmax, that one was bullshit. So complex. Okay. First, I think we're going to have to... No, we're not playing chess. The legacy of Tom Cruise is being taught in college security courses. You too can have this kind of skill. All right, let's first figure out, let's get it to work for batch gradients first. All right, so like let's do 0, 1, 2, 3. That doesn't work. Grad can only be implicitly created for scalar outputs, and that's because we got to stick a mean on there. That's a lot of feet. Wait, what is, I commented out that print. How's something still getting printed? Oh, loss.grad and out.grad. Oh, look at that. Wait, is that really true? Oh, that's -1. Why is it -1 if I do mean and not -1 if I don't do mean? It's still -1, never mind. A loss function using NLL loss. I mean, that's just going to change the magnitude of the gradients, but we can just do that. Okay, so that's a picture. Let's confirm that the two pictures look the same. I'm using SAMP2. Okay, those pictures look the same. Okay, now if I do SAMP01, oh, it does that. Oh, this we just have to make length of SAMP. Okay. Operands could not be broadcast together. Oh, that's... What? Dot reshape. Oh. Whoa, look at that. That's trippy. How'd that even happen? Okay, so that's what 0, 1 looks like. Let's see if 0, 1 looks like that up there. No, they look totally different. Well, I mean, that D out is different. Now those are the same. I don't know, I kind of like mine better. Shouldn't it kind of just like stack them? I like my gradient better. Can someone tell me why it's not better? They're stacked more fairly, it seems. You know we love fairness on this channel. Oh. Okay. So this is one of the problems. Actually, my DXLSM is just wrong. It's not even the right shape, is it? 2,10 is right, but yeah, we want to do sum axis equals 1, I believe. Yeah, and then we sum axis equals 1, and then we put a reshape there. Okay, good. Now those look the same. Ah, okay, now it looks the same. Oh, that was really easy to make work. Overflow encountered in log. We can actually fix this too. There's a stability hack for this where you subtract. Why is it printing stupid scientific notation? It's really insisting on scientific notation. Yeah, you want to do like log sum exp. Oh, log add exp. Oh, it only handles 2 inputs. Wow, that's stupid. What's the numerical stability trick for this? Overflow encountered in log. See any overflow? Do you see an overflow? Those look like very reasonable things to take the log of to me. I think I can do something like, I want to subtract the max. Yeah, because X gets big if the numbers are big. So if I subtract, this works out to like the same thing mathematically. That doesn't look like the same thing. Subtract them in, add them in. Something like that. Log sub x trick. Oh, we subtract c, okay. If we set c to the max, so the way to do this, if we want the same value, and so my logs don't complain about overflowing anymore, is we say xl2.max axis 1 dot reshape oh wow, yeah, it's really just the max. Okay, that looks the same. But now if we want that fast one, we can say we'll call it C. Why does that not match? That matches. Oh, because we don't want to reshape it there. Only want to reshape it there. Perfect. Beautiful stability hack. And yeah, the derivative doesn't do any logs, it just takes an x, so there's nothing I can do about that. Probably. There probably is, but you know, that would involve knowing calculus. And, well, you know. Alright, so let's check a bunch of gradients now. Yeah, that looks like, wow, look, it's like learning. Look at how much it's learning. Look at all that learning it's doing. Oh, that's beautiful. Those gradients are beautiful. Alright, let's check it down here. Looks the same. Oh man, imagine Newton had PyTorch. PyTorch, Newton. Lost dot grad is just 1. I don't really understand why it's 1, but we'll understand someday. We don't need those anymore. That's all right. Okay. def forwards, backwards, x, y. Go what? My posture? Yeah, no, it's not good. I'm hunching over the computer. This chair doesn't have a headrest like my gaming chair. Yeah. I don't know about these this Hugo Boss chair. Herman Miller. I get those guys confused. Okay, so these are the only learnable parameters in the model. So we can just return them. Beautiful. All right, let's get my Xavier inits to match. You know, it's really important how you initialize your networks, because if you don't initialize them right. Torch, linear, init. Linear one is here. Init Caming uniform. Wow, I don't even know. What's a caming? That's some crazy kind of noise. Whoa, is caming the new Xavier? H is just the... Wait, what? I think it's called randan and numpy actually too. Okay, randan. Okay. Times math. Wow, caming. crazy. I'm not even going to start on how that works. But we will test it a little bit. Yeah, those numbers look pretty similar to those. Okay, so what can I copy? We're going to want that same code. That can come with me. L1 equals caming L1 dot shape 0. I could just say star L1 shape. Reinit. Okay. Now we want to do forwards, backwards, but not on the test. We'll just copy that too. Nah, it's fine. Y train. L1, L2. No, sorry. DL and DL2. One of these days we'll write Adam. All right. Runs fast. Now we want to compute the loss and accuracy. Oh, well, actually I can just compute the loss. What kind of crazy high losses? Is that right? Is my log sum X? Oh, it's because it's not initialized. Well, those are actually reasonable losses. The only question is, why is there no loss for the first one? Weird. Okay. So those are actually reasonable losses. Okay, so we're getting an accuracy now of 9%. That all makes sense. Now, we want to write SGD. So we have the derivative, so SGD just is mostly, this one I actually think I can implement from memory. Oh, we have to put our learning right. We're not going to use any momentum. Okay. That's X loss. I don't know, we can now put XL2 as well. Which is the out. np.argmax XL2 cat. Oh, we do need. Okay, now we need to copy the appends. And we can copy that line where we update the description. Posture. Update the description. And then we'll copy the code we plot them to. Okay. So of course nothing gets better because we didn't actually implement the update rule yet. And the update rule is L1 equals L1 minus LR times the derivative. Oh, that looks like decent accuracy. Let's evaluate it. Just call NumPy eval. 85%, that's pretty good. I mean, it's not as good as Torch, but I don't know. It's not supposed to be plus, is it? Definitely not supposed to be plus. Wow, that's big negative numbers. Yo, last time I saw numbers that big. Okay, so the only question is, why is it shittier than Torch? Should be pretty much the same. Let's just rerun the whole kernel. Did I do my K-ming initialization wrong? Did NumPy forget what the square root of 2 was? It's a pretty common thing to forget. We're so close. Like, it's almost the same. And it's still learning. Maybe we'll just let it learn. Maybe it learns slow, you know? Maybe, yeah. PyTorch has 160 IQ. NumPy only has... This is probably due to some numerical stability stuff. Like, they're always talking about these kind of things, and no one ever takes them seriously. I wrote SGD. Oh yeah, look, 93. It just is slower. That's so weird. My batch size is 128. That's the same, right? It learns, it just takes longer. Picking random stuff. Oh, len samp. Oh, look what I did. Yeah, oh, so that was, oh, I had a learning rate that was effectively 32x too high. Let's try it now. It's learning faster, I think. Well, it seems like it's learning slower, never mind. Well, it doesn't learn at all like that. Okay, well that was a bug. Yeah, the laptop fan's going, you know? Takes a lot of math to learn deep. What other bugs did I write? You know, that's the problem with optimizers. You write bugs and they're impossible to find because the optimizer just optimizes over them. You know, I guess I didn't check the magnitude of these gradients. I mean, imshow is gonna hide all that from you. Let's check them. They're very different orders of magnitude. Actually, they're very different. Oh no, never mind. Oh, they're similar. They're slightly different. It doesn't just look like a scaling thing. They're different. They're actually different. They just look similar. The means are the same, though. I'm going to add these here. I mean, transpose, obviously. I think this is just numerical instability. Like, PyTorch works really hard on this stuff. Huh. No, the L1 weights have similar, but the L2 weights are different. This is useless. What is numerical instability? It has to do with if you do like yo, you ready for some craziness? Let's try 64. Does the same. All right, should we cheat and add momentum? Little cheating? Only little. Well, let's just see if it fixes it. One of these days we'll write No, I think you know what? I think 86% is just what we deserve. What actually? NP set seed. Is it reproducible? It is. Let's remove the logx sum hack. Does the same. I didn't do anything like leave SAMP anywhere in here, right? This is one of the downsides of notebooks. You know what? Let's restart and clear output. And let's just try the NumPy ones. Let's not import Torch up here. That kind of ruins it. We don't even have Torch imported, okay? Oh, that wasn't NumPy. Whoa. Actually, this might already be... Oh. Well, okay, never mind. Oh, it already is float 64s. Maybe float 64 has made it worse. And then got an unexpected, really? Do I have a fig size somewhere in here? I'm sure I do. On that stupid crap. No other fig sizes. All right, chat. I'm pretty happy with this. I don't know why it's not as accurate. There may be bugs, but like just the fact that the two gradients aren't exactly the same. I'm pretty happy with this. Even though we only got an 85. Oh, Torch uses momentum by default? No, I turned it off. You know, it gets there, it just takes a little longer. I don't know, let's give it 4,000. Let's make the batch size smaller. And it gets there. Maybe 2,000 is fine. Mm, 2,500. Let's seed hack. Let's mess with the seed until we get a good one. Yeah, just like real deep learning papers. Yeah, that's right. I have so much compute that I'm willing to burn to get a better accuracy. Oh, look, this one's better. Over 90% with hand-coded stuff with Numpy. Wow, Numpy. Perfect. Is there any other like hacking that SGD is using? No. Is my initialization bad? Well, here's something we can do. What if I don't init the things? And I just use the ones from PyTorch. Ooh, look, it improves them. It's possible that their initializer is just better than ours. Initialization is super important. Let's just run that. Oh no, I don't want to run that. I actually just want to run model equals BobNet and then, yeah. Okay, so that's junk, but now we don't do the init. Huh. It's good now. It's really just all the initialization. My initialization isn't right. That's wild. Stupid caming initialization. It's not right. Look, now it learns. How could it be wrong? Look at that. If I steal the weights from BobNet, it learns. Oh, wow. Wow, that really makes you think how important initialization is. Wow, that's it. That's using uniform noise. If this is what changes it. Well, I mean, I already know it's that. Yo, that's even better. I think I've managed to beat PyTorch with my sick uniform initialization. Look at that. We're getting 96% now. That's insane. That's just insane that that does it. And none of these match PyTorch, which does something totally different. Use caming initialization, get crappy evaluation. Use uniform initialization, get strong. But none of those match PyTorch, which is something entirely different. It's entirely determined by your layer initialization. Ugh, I can't get over this enough. PyTorch, linear, layer, init. Only convs do. Is this supposed to be m times h? I feel like it's supposed to be m times h. And that was just bugged. 6 divided by, I don't even know. I don't even know. This doesn't make any sense, but that one's pretty good as well. Okay, they're all good. They just need to be scaled right. Yeah, somebody forgot a times h, I think, in that crappy example that I copied. Wow, NumPy's better than PyTorch on both of them. But what is PyTorch using? I don't know. This is a great mystery of the future. But for now, let's run our notebook, sit back, and enjoy our 96% accuracy. Using 2 linear layers, we've actually beaten PyTorch in accuracy. Didn't even seed hack, changed it back to 1337. Everyone knows that's a no number up my sleeve seed. Beautiful. PyTorch, 93%. NumPy, 96%. Yo, and what if I make it float 64? I bet it's going to be even more accurate. Same accurate. Did that look less noisy to anybody else? What if I make it float 16? More accurate. Wow. What if I make it uint 8? Uint 8 is weak. Float 16. Look, float 16 is such a winner. Float 16 just wins. Note, add more accuracy with float 16. All right, kernel, restart and rerun all. Let's commit this. I'm very happy. We got over 96%. That's accuracy that exceeds PyTorch's accuracy because we're using good initialization functions. Initialization is super important. When you do your deep learning, always remember that. That's the lesson we learned today. And we're getting 96.3% of accuracy. We'll do very quick questions. No, we can't be overfitting. This is the test set. We train on the train set, and we test on the test set. NumPy eval tests on the test set. Oh yeah, look, PyTorch got a crappy... PyTorch sucks compared to NumPy. I'm going to write deep learning, but it's going to be accurate. No, what is this? Both 1,000. I did 1,000 for both. PyTorch is this noisy crap, which actually makes me wonder if I wrote bugs. But actually, you know what we can do? We can use layer init on PyTorch. Just for fun. Initialize ND's parameter weight. What can I say? Dot copy. Torch assign weight. I don't want to do that. I want to copy. Maybe just this. Can I assign a numpy ND? Oh, I gotta make them tensors. Oh, we gotta transpose them, don't we? Cannot optimize a non-leaf tensor? What? Leaf. With torch no grad. Oh, now it matches. Yo, whatever Torch's default initializer for layer is. Pro tip. If you like accuracy, next time through the notebook, consider pro mode wait init with numpy instead of beta torch init weak crap. No, we don't want to say it. We want to say instead of beta torch init weak. Yes. That's what we want to say. Oh, yes. Virgin Torch versus Chad NumPy. Oh, that's, yeah. Consider Chad mode, wait, instead of Virgin Torch init mode. Perfect. All right, I think we can commit this. I'm very happy with the work we did today, boys. And very strong accuracy. To do. Why is Torch linear init bad? Is 100% accuracy not possible? Oh, well. I mean, that's a philosophical debate. On the test set, of course it's possible. In life and in general, 100% accuracy probably means you have an evaluation problem. NumPy accuracy greater than Torch accuracy. All done. Can you feed your own drawing to test? Okay. How do I make a drawing? Okay, fine. Guys, what number should we use? What number should we use for our own custom drawing? No, we're not using paint. We're using... Okay, can we get a vote going here? Let's draw a nice 3. All right, 4. All right, we'll draw a 4. All right, I'm sold on a 4. Okay, so it's 28. So that means we got to go 7 by 7. For fun, can it recognize 4? Okay. So we're going to draw a nice 4. And we're going to go through all by hand, and we're going to compute this, and then we're going to see if we've written high quality code or not, or if we've really just overfit to junk. We can improve our 4. This 4 looks upsettingly like a 9. All right, should we go to 14 by 14? No, 14 by 14 is too much. That's a good 4. If it doesn't recognize that as a 4, nothing's a 4. Do people believe in my 4? All right, that's a good 4. Okay, so let's resize it. How do we resize it quickly? We're gonna resize it. How do I resize? Resize. In a one-liner. Well, it's not, so it only takes in things that are 28 by 28, so we got to resize it. That's not going to work. I want to stack those all. I want to concatenate them. Upscale to 28 by 28. Okay, you ready? We're gonna write out the whole thing by hand. We have an m dot reshape All right, let's take a look at the forward pass. Dot L1. We gotta do a ReLU next. np.argmax_x. Oh, it's a 9! It's a 9! Oh no, it's a 9! That's really a 9. Let's change it until it's not a 9. I mean, to be fair, it kind of is a 9. Nine. It's a 9! I mean, like, you understand where it's coming from, right? Is that more 4-y? Oh, now it's a 4. Yeah, now it's a 4. That's right. Yeah. What is it? Wait, how do I get large text? IPython notebook large text. Never mind. I don't know how to get large text, but let's run it again. Oh, just put a 4 in the output and use 4 backwards to get the canonical 4 pick. Yeah, that's not as easy as you think it is. All right, let's draw a 2. You know, I don't like 4s. They look too much like 9s. Who let me convince that it was 4? Okay, fine, at 3. 3s are good. That's a nice 3. That's a 5. Damn it. Deep learning doesn't work. Still a 5. We're putting it back to 4, and we're just calling it. Deep learning doesn't work. No, we like to end things on a positive note. Let's draw a better 3. That's a 4. These are all 4s. Wow, really, that cross over there really makes it a 4. A nice 4. Oh, someone wrote a nice 4. Oh, a user 4. No, your 4 is too large. All right, we will try your 4 just briefly. Just to see if it works. Oh, that what the hell kind of 4 is that? List has no attribute reshape. That's what kind of 4 that is. Your 4's not even the right size. It's 812. You have one too many zeros over here. Oh yeah, why was I trying to draw my 4 the stupid way? What if I just draw it like that? I can't believe I'm deleting the zeros in your example. And you know what the worst part is? I'm not even 100% sure that I'm deleting the right zeros. Oh, but now I accidentally deleted one of those. No, I deleted the wrong zeros. It's a 7, okay? That's not a 4. But you're right. What if I draw the 4 like this? That is undisputably a 4. Beautiful, that one's a 4. I'm very satisfied with that. We're gonna leave it at that. I bet even if I delete this, it'll still be a 4. Oh yeah, that's a nice 4. Ugh. Oh, how does this 4 look? Oh, that's an even more beautiful 4. Should we even bring it closer together? Let's bring it closer together. Oh, that's a 4. Why did you let me draw my 4 with the slant? That is a solid 4. It prints 4. Let's see how convinced it is that that's a 4. Oh, super convinced. Wait, what? Isn't that number bigger than that number? 0, 1, 2, 3. Oh, 4 is over here. Oh, I didn't count right. Oh, look, it's so convinced it's a 4. It might be a 9. It also might be a 3. And let's see what number it's definitely not. It's definitely not a 2. It knows for sure about that. Okay, let's rerun this. Let's commit it. And then that was today's stream. That is a beautiful 4. Except we actually have to change this to 4. Train, evaluate, 4, 4. Love it. Look, it knows what a 4 is.
Very impressive.
You want to draw a number? Or are we done? We're done. We done? It knows 4. Thank you all for watching, everybody. Should we do questions?
Yeah, give me questions.
Want to do questions? Who slept for? Leaney's left?
I don't know what's going on.
Oh, I didn't even know that.
I was just coming to flip them away.
I'll look through you.
You want sauce on them?
It works with 4 as long as you draw 4 to the. To be fair, the other 4 did not look that much like a 4. I only had 7 by 7 to work with. Oh, the Quest jailbreaking stream. Well, I don't know about that. You gotta go. Who even gets out of bed for 5K? I will give you an exclusive license to this 4 recognizer for only $500. It can be yours. I'll take it off the internet. Just like that Wu-Tang album, it can be yours. Nobody draws 4 with a slant. Exactly. I don't know what I was thinking. Of course I thought it was a 9. You know. Will I raid someone after finishing stream? To be honest, I would, but I don't know how. I'm not a very good Twitch. How much for 5 recognizer? I don't know about that. What? Are you gonna shower? All right, and then I'm done with streaming. I'm done with the computer for all day.
Yeah, I'm gonna make
Oh, thank you. Wait, is there water involved in this sausage?
I'm putting boiling water on them so it'll heat them up a little.
Wow.
Is that on the microwave?
Raid awkward chats. All right. You're not shilling for yourself, are you? This is an ad. I'm watching an ad right now. Investigating info. This sounds too much like doxing. I will have people to raid one of these days. You just got an ad for this stream? I'm sorry. We got, I know the Oculus is challenging me. Yeah, we got things to do. Oh, yeah, Lana Lux. Yeah, well, that sounds good. Lana Lux has raided me several times. She's streaming right now. This channel is intended for mature audiences. Start watching. What? I got an ad again. Wait, can I not? I already have a raid in progress. All right, excellent. Passing on the viewers. Enjoy, everybody. Thank you all for watching. I hope to see you here again next time we stream, and we'll do something else. All right, bye-bye. I got things to do today.